logs and introduce the 4 basics of weight. Today we're going to talk about weight and balance. That's important because if we got too much weight in the tail, the airplane pitches up. And if I get too much weight in the nose, oh yeah, the airplane can pitch over and all the stuff can come out of the floor. And if I don't have the balance exactly right, heaven only knows what's going to happen to the airplane.
Do you remember when we used Newton's second law, force equals mass times acceleration, to determine my weight? Well, actually, what we were measuring is the force I exert on the Earth. And likewise, according to Newton's third law, the Earth exerts the same force back on me. Well, what if we use 2 scales instead of 1? And I put a foot on each scale? Well, I have 75 pounds here and 75 pounds here. Adding them together, I get to 150 pounds. So what we're really measuring is the force I exert on the Earth where I come in contact with the Earth. That's how we weigh an airplane. We put a scale underneath each wheel, add the weights together, and get the total weight of the airplane. And that's pretty simple. But determining how that weight is distributed over the airplane, that's a little bit more difficult. The weight of a plane is distributed in various places. Some have one engine in the nose, while larger planes have engines on the wing. Some carry fuel only in the wings, others carry it all over. If I wanted to lift the plane by a single cable, where would I place it? I'd want to keep the plane relatively level when doing this, otherwise all the people would fall towards the nose or tail. So what I really need is the balance point of the airplane. On an airplane, the balance point is called the center of gravity, or CG for short. Instead of using a cable to lift the plane, we know lift is created by the wing. Therefore, it stands to reason the weight must be concentrated where the wing lift is located. Knowledge of the CG location is critical for stability and control of an airplane. Let's be sure we all know what we mean by the word control. It's the ability to generate movement through the application of forces. Now, on occasion, I've leaned back in my chair, but if I lean back too far and can't control the chair's movement by shifting my weight, well, you get the idea. That's the same basic principle we use to control an airplane. Simply stated, the movement of the airplane around the center of gravity is controlled by surfaces on the wing and tail. For a given speed, it is the size of these surfaces and how much they are moved which determine how much force is created to control the airplane. If the surface is too small, not enough force is created and the airplane won't respond to inputs. If the surface is too big, we can get too much force created, which can lead to over-controlling. Here you can see how over-controlling can get a pilot's attention rather quickly. So determining the size of a control surface all begins with determining the center of gravity location. There are 2 ways of determining the center of gravity for any irregular shaped object. And believe me, I've seen some really irregular shaped airplanes. To help demonstrate one method, we're going to employ one of the flight test engineers here at the school, Al Wallace, to show us how. Al?
All right, what you see here is an irregularly shaped piece of sheet metal, and there's holes all over the place here. We can use a little hook anywhere among any of these holes we like and hang the piece of sheet metal. Now, the center of mass hangs directly below the pivot point here, somewhere along this line. To find out what that line is, we can employ a simple carpenter string. Just hook it right there at the same pivot point, and then Mark is going to hang that down straight, and we'll try to stop it from oscillating. And Mark, I'll just squeeze it in place there, and if you'll snap that string, voila, a line saying that this is exactly the vertical line down from the hinge point. Now, we can go to any other of the holes drilled in here and do the exact same test. So I can go over here to this corner, pick it, and once again, the center of mass hangs directly below the pivot point. Let's find out what that line is. And we'll let that thing stop oscillating. Okay, Mark. Now, according to the theory, no matter which angle we look at it, no matter which hole we drill, that center of mass will always hang below the pivot point, and it'll always end up right there at that cross. So to prove that that's the center of gravity, I'm just going to take my thumb, put it right there on that spot, and hold it. Voila, the center of gravity.
I wonder if we can do that with an airplane.
I don't think so, Mark.
Well, in order to figure out how to calculate the center of gravity of an airplane, let's go back to the playground and start there. Hi. Most of you have ridden a seesaw at one time in your life or another. And you remember how if the guy at the other end didn't weigh pretty close to what you weigh, the board would tip. If you weighed more, the board would tip towards you. If they weighed more, it'd go towards them. So how did you balance the board to make it enjoyable? Well, the heavy person can slide towards the pivot point, or the lighter person can slide away from the pivot point. That way, the forces would be equal. We do basically the same thing with an airplane, only instead of shifting people around, a lot of times we'll shift fuel or cargo. In physics, the length of the board on each side of the pivot is called the arm, and the pivot point is called the fulcrum. I place a weight, or more correctly a force on one side, then I must multiply the force times the arm to get what is called a moment. This gives us an equation that can be written as moment is equal to the force times the arm length. Only when the opposing moments are equal will the board remain level. Newton's third law at work again. Let's go back to the seesaw and put in some numbers to illustrate the problem. Suppose I have a 10-foot board and place a 155-pound weight at one end. Then the arm between the fulcrum and the weight is 5 feet. This gives a moment of 155 pounds times 5 feet. Now, if the other side has a 170-pound weight, where on the board should it be placed? For the board to be balanced, the two moments must be equal and opposite. So balance equation can be written as 155 pounds times 5 feet is equal to 170 pounds times A feet. Solving for A gives 155 pounds times 5 feet divided by 170 pounds, and that'll equal A feet. So A is equal to 4.56 feet. Now, a test pilot or engineer always verifies results, so let's put these numbers back into the equation to make sure they work. We had 155 pounds times 5 feet should equal 170 pounds times 4.56 feet. Then performing the math, we see that 775 foot-pounds is in fact equal to 775 foot-pounds. That checks out okay. But up till now, we've been using the balance point to determine the length of the arm. In the real world of flight tests, we're trying to find the balance point, or the center of gravity of the airplane. So the arm lengths have to be measured in reference to something else. Well, that something else is called the reference datum line, and it's usually located at the nose of the aircraft. You know, determining the center of gravity of an airplane is crucial in flight tests. NASA uses this high angle of attack research vehicle to check flight control movements and new control laws. If they don't know where the center of gravity is, they don't know if they're going to have enough control power. So let's use the reference datum line and compute the center of gravity of this high angle of attack research vehicle. To do this, we're going to use the relation that the sum of each moment equals the total weight times the arm to the CG. Look at it this way. The empty plane was weighed and found to have 6,000 pounds on the nose gear and 10,000 pounds on each main landing gear. Then the total weight is 26,000 pounds. Then the CG location can be found by performing the following calculation. 6,000 times 18.2 plus 10,000 times 36.2 plus another 10,000 times 36.2, which gives us a total weight of 26,000 pounds at an arm length of A, because we don't yet know where the center of gravity is located. Performing the calculations in the same way we did for the seesaw, we can see that the CG is located at 32.04 feet from the reference datum line. It's no surprise the center of gravity falls on the wing of the aircraft, and the CG will move in flight depending on if the fuel burns from the forward or aft fuel tanks. But the designers accounted for that and has given us a range of CGs where we can still have flight controls to be able to maneuver the airplane. Let's look at the pilots and fuel in this airplane and recalculate the CG and see how it moves in flight. Using the same plane, let's add the pilot and fuel. Pilot has a moment of 2,325 foot-pounds, which comes from 155 pound times an arm of 15 feet. The forward fuel tank has a moment of 53,750 foot-pounds, and that comes from 2,150 pounds with an arm of 25 feet. Now the rear fuel tank has a moment of 132,311 foot-pounds, which is the result of 3,620 pounds at an arm of 36.55 feet. And adding this to the empty aircraft, recall that was 26,000 pounds and a total moment of 833,200 foot-pounds. The flight-ready CG is approximately 32 feet. As you can see, adding the fuel and pilot only moved the CG about 4/10 of a foot. So the balance change is negligible. But what happens if we burn all the fuel out of the aft tank and no fuel out of the front tank? Subtracting the rear tank's moment and weight from the totals, we get the new CG location. Before it moved, the center of gravity was located on the wing at a point where the lift is being produced. But now it's moved forward. So in order to keep the plane level, we've got to create a balancing moment. That balancing moment comes about as a result of a down force on the tail. We lost a total moment of 132,311 foot-pounds when the fuel burned out of the aft tank. Since the tail is 51 feet from the reference line, then a force of 2,594 pounds must be added to the tail to keep the CG from moving. Can you imagine what would happen if the tail wasn't large enough to compensate for the fuel burn? Did you enjoy all those calculations? Well, that was a small airplane. How about this? 4 engines, lots of fuel, hundreds of passengers. How would you ever figure the center of gravity of this thing? Many large aircraft have a weight sensor in each landing gear. That information is all added up and sent up to the cockpit. The computer takes the information from the landing gear, calculates the center of gravity location in the same manner that we did, and then if it's not within range, moves fuel around until it is. Unfortunately, the computer can't change the weight, and the designer of the airplane has to learn how to get that weight in the air. That's a subject for next time. See you then.